I thought I would start today by giving a short feature before the main event. And I selected 5 of your plots from the second homework assignment that I wanted to just show you, as each of them has a slightly different thing that I thought was really nice. So I just thought I would feature some of your work. And also, this is a way for me to strongly suggest that you start thinking about how to make plots of your data, to uncover the structure, to explore the data for your projects. A very big part of this assignment, the project assignment, will be making informative, rich visualizations of your data. So here's the first plot, which I think someone took a screenshot and it was too blurry, but this is about music and who purchases music. And you can sort of see that this is one of those jiggle the baseline problems where it's really hard to tell what's happened with over time. And this is what the Diana and Assis did. They, instead of stacking it, they looked at each of them separately. And so you can see that the 40 over group became the much larger percentage of those purchasing music. And they've got these nice markers saying first online music downloads versus legal online purchase. You know, so sort of events in the music sales industry that would affect who's paying for music or not. So I thought that was very nice. Here's another one, which is a U.S. crime rate per 100,000 population from the 1960s to 2005. And this is actually a very nice plot as it is, showing what is trends over time. But the students who worked on this took a different perspective, and I just thought it would be worth showing you. This is Travis and Ona's plot. They looked at it in terms of what's the relationship between unemployment rate and the crime rate, and saw that as unemployment increases, crime tends to increase as well. They fit a line through it, and we're going to be talking more about sort of fitting lines to scatter plots later on. So what I liked about this was thinking that they were able to think about the data in a different from a different viewpoint than what was originally provided. So although this was one set of time series plots, the actual data on Many Eyes had several time series plots, and they wanted to figure out sort of what happened to more than one variable, and so they made this scatter plot. Here's another sort of jiggle the baseline problem, where there's a slight sort of green thing, which maybe you can detect or not. And this is Johan and Marco's work. What I liked about this in particular was that they were able to get markers that indicated things that were directly would impact what you see in the plot. So immigration acts, they put markers for these immigration acts, and you can sort of see this peak in the number of immigrants is, for the first one, is right at the one immigration act, and there is it's not the case for the second one. Here's another plot, which I thought was that one group worked on, and this was trying to present popularity of different kinds of games, PlayStation games, Xbox games, etc. And this is what they turned it into, is they said, well, let's try and compare PlayStation and the different kinds versus Xbox and X360 and other Game Boys, etc. And so the box plots are taking the ratings of the various people, and so you can see the spreads. You can make comparisons across types of consoles and across sort of improvements within the console. My one criticism of this is that the color actually has no meaning in this particular plot. What would have been nice to see is if all the PlayStations and all the Xboxes were the same color, and then it'll be easier to compare the manufacturers. This is my last one. This is one of these side-by-side bar charts, which makes it really hard to make a comparison. And they turned it into a mosaic plot because they had two categorical pieces of information. They had education level and race. The colors they actually look better there than here. They're really bright on my screen. But then it becomes things like, you can't read that on the projection, but the bottom green color is Hispanic, and you can see that they're disproportionately represented in the lowest education level bracket. And the top is white, and you can see that they gradually get more represented as education level increases. Yes? I think the width is the proportion of the population that are in that category, right? And so the biggest one is high school. And the one all the way on the, I can't quite read the one all the way to the right. But yeah, so the biggest one's high school, the next biggest one's college. Okay, so, and there were let me just say, those are 5 that I chose. There were it took me a long time to pick ones. I wanted to pick various ones to show you the spectrum of the kinds of things that you all did. And many of them others were really quite nice as well. Okay, so we actually didn't get to confidence intervals on last Wednesday, and we are definitely going to get to them today. And we're going to do some demos to get to confidence intervals. So this is a really simple example, and we're all going to carry it out in class as well. So let me start with one of these guys. So I'm going to demonstrate it first, then I'll come back to the the projector, and we can. I'll show you the calculations in more detail, and then you guys are going to have a chance to do this as well. So here's my population. It's a bunch of Starburst candies, and there are 88 candies in my population. Those are my observation units, and they're also my sampled units because I am able to observe, or my target population and my sampling frame are identical, and they are all responding, and so I'm in that nice world that we always like to be in, which is where we can ignore all of the issues about worrying about not getting everyone in our sampled population and that sort of thing. So what I'm interested in is the proportion of yellow starbursts in my population. So I don't know what that proportion is. That proportion has a technical name, which is my population parameter. And so this population is so big that I can't simply, which is not actually the case here, but it's so big that I can't actually take a census. And so what I'm going to do is instead take a sample. So I'm going to sample by drawing 16 from my 88 and counting up, or finding the proportion in that 16 that are yellow. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I need 6 more. And I'm cheating a little bit because I know what I should be getting for my response based on the data that I've already prepared in my PowerPoint. So you wouldn't sample by looking into the bag and picking them out, which is what I just did. But there's my sample. Can you see the colors? No. I Okay, kind of. Actually, you sort of can, but I think this is so bright. Does that help? Yeah. Okay. That's even better, right? Yeah. Okay, so we would separate out our yellows from the rest. So the others, I don't care what color they are. I want to know what proportion of yellows do I have. I found 5 yellows and 11 not yellows. So the proportion in my sample is 5/16, which is 0.3125. And so that's what I've observed in my sample. And now I want to go about estimating what the proportion is in this whole bag. So the typical way to do that is to say, well, my sample should look like my population. Why? Because I took a simple random sample. So that probability mechanism that I used tells me that my sample should look roughly like my population. So my estimate for the population is 5/16. But now I'd like to tell people what kind of error is attached to my estimate. So you have a sense of how accurate I think my procedure is. So that error should be, well, if I, from a probability perspective, what's the probability distribution of the sample proportion? Now, the sample proportion is just an average, right? It's an average of 0 ones. So that's sort of asking, what's the probability distribution of the sample average? So you all know what that is, right? You've worked on that painstakingly on your last homework assignment, which hopefully this is a way that we can elevate past the code and how do we get the code to work to what did we see in that, what did we learn from that assignment. So I'm talking about questions 3 and 4 on homework number 5. What did you find was the sampling distribution or the probability distribution of for either box of the average for that box when you drew without replacement from the box? What were those probability curves you were plotting? What did they look like? Yes? They looked normal, roughly normal. They weren't exactly normal, but they were roughly normal. And as you got a greater and greater sample size, they looked more and more normal. A sample size of 1 wouldn't look normal unless the population itself looked normal. But as you draw more and more times, the central limit theorem says that the average, the probability distribution for the average should look roughly normal. And questions 1 and 2 help to figure out what the spread of that distribution was. And you know that that spread followed that particular formula of the SD of the box divided by the square root of the sample size times the finite population correction factor. So I can make that calculation now. Well, I can't. I don't know what the SD of the box is. So what do I do? If I want to say, hey, my estimate is 5/16, and the error that I would attach to that estimate, which tells me how accurate I think my estimation procedure is, what should I do? I know the sample size is 16. I know the population size is 88. So I can figure out that finite population correction factor. And I know how to divide by the square root of 16. But I need that SD of the box. Yeah? Good idea. Well, since my simple random sample says that my sample should look roughly like my population, why don't I take the SD of my sample and plug that in for the SD of the population? And that's what we do. So in this 0, 1 case, that would be root 5/16 times 11/16. And I can construct an estimate for the error involved in my estimation process. So I'm now going to go back to the PowerPoint here. And and then you guys are going to carry out where'd my PowerPoint go? Are going to carry out what I just did. But first, I'll just go through it again. So my population, Starburst candies. The parameter of interest, that's the unknown piece of information about my sample, or about my population, excuse me, is the proportion of yellow candies in the population, and my population size is 88. This is my sample. I wound up with 11 non-yellows and 5 yellows, and that's the distribution of my sample. From that, I'm going to make an estimate for the population. My sample size is 16. I observed 5 yellows, so 5/16, 0.3125 is my sample proportion. My sample SD is 0.46. So notice that the sample SD is different than the standard error, also known as the standard deviation for the sample average. So I only use SE when it is referring to a statistic that I'm calculating and I want to know its probability distribution. Okay, what we don't see is what's in the box, and I'm not going to show that to you. That went by really quickly because that's what you're going to find out when you do the sample yourself. Oops, sorry. And what I want to do is we know, as we just said, that the central limit theorem tells us that the sampling distribution follows a normal, with the center is the proportion of yellows in the population, and the spread is the population SD divided by the square root of 16 times the finite population correction factor, which is 0.91 in this case. So the approximate SD of my sample proportion, my sample average, is when I plug in the sample SD for the population SD, and I get 0.11. So, so essentially, I want you guys to do this. Now, each of you get your own sample and compute your sample proportion and your sample SD, and then the SD for the sample proportion. So to do that, I have duplicated, I've cloned my population so that I have 5 of them. And I'd like you guys to work in pairs. And I've got copies of this sheet. Oh, you don't. You're not seeing that sheet. I've got copies of this sheet for you to fill out. So I've got 5 of these, and I'd like you to work in pairs, but that means also that you're going to need to sort of get together. Pairs or triples, whatever works for you. I'll put one of these in here. All right, so, yeah, thanks, Mike. Do you want to hand out 2 of these? So how about you guys here? I'll give it to you, Sharada. The set of you guys work on this one. And I'll give you this one. And can you guys from the front come back? And so work in pairs, so you have to take turns, basically. And who's got? How about here? I'll give it to you. And so if you guys can work together as well. Sample size is 16. So I want you to fill in this sheet as you do this. And we only need roughly 1 per pair, but if there's more, that's fine. So fill in the sheet. So that's why your partner can help you fill this in as you do this. I was trying to, if I have extra, I'll come back, but I want you to share them.
Did you finish the first one?
So we've got some extras if anybody would want, who doesn't have one, would like one. We've got a few extras if you want. Does anybody want one? Do you want your own? Do you want one? Did one between the 2 of you or 3 of you, and then move it to somebody else? Do you want one, Warren? Or are you set? Okay. Replace your sample before you pass it on. You'll have a chance to have some afterwards. Yes?
Our sample was really funky. Is that?
That's good. I want that to happen. But where's your population? Oh, there. Okay. All right. Did you get one? Yeah. Okay.
It's supposed to be 11 again?
No, could be anything. Yeah.
All of them?
No, the sample size is 16.
I know.
Okay, sample size 16.
Sample size 16. That's the one thing you have to obey.
How did you get this SD right here?
Well,
Square root of-
if 5/16 times 11/16, I might have made a mistake.
I was just wondering what, like, that formula is.
Oh, that's P times 1 minus P.
Oh, okay.
Remember
oh,
it was 0, 1?
box.
Yes, right. So put your sample back in the box before you move it on to give to someone else. You're supposed to, you don't keep your sample. You're supposed to put it all back. You can, well, there'll be time for that later. So essentially, I want you to fill in the middle column. What's your question? You're both looking at this like...
Okay, that's the SD, right? But we're effectively doing a hypergeometry test. So
There's no test here. There's no test. Yes, but we're not testing anything. We are estimating now.
so we don't have to do like a multiply by FPC.
Yes, we do, but that's not about testing. Right. So that's just the sample SD. Now when we go over here, actually we can go over to the bottom part and say, we don't know this right now, but they're going to estimate the SD of the sample average would be approximately the sample SD square root of 16 times the FPC, which is square root of 88 minus 11 over 88, minus 16, 88 minus 1. So just to make it easier for you, that's this of the sample average, right? And just to make it easier, square root of 16 is 4, and the FPC is 0.91. Okay? So this is 0.91. Can you explain why that is? Why what is? That's what you derived on your homework. And I can do it, but it's a pretty complicated calculation. So that's the beauty of doing it by simulation, is you can discover it through repeated trials. If that's something that you prove in Stat 134, and it's given to you in Stat 20. No, that formula, capital N minus little n, population size minus sample size divided by population size minus 1, square root of the whole thing. if anybody's really interested in this, I am happy to derive it for you outside of class.
Professor, I just had a question about the sample. Is it supposed to be the sample size times, like,
Sample average,
No,
if
no,
it were, oh,
for sample as was I consider root of sample size times e times 1 minus b?
no, the sample SD is about your sample. So it says, what's the typical deviation of values in my sample from the sample average? And so that, if we did it by the formula, it's a list of numbers, basically. It's 5 ones and then 11 zeros. And so the SD is the SD of this list of numbers, which would be the square root of 1 over 16, the sum of the actual individual numbers, minus the mean, which is 0.31 squared, which we know in this case reduces to just reduces to this formula here. So the sample SD says, what's the variability I expect in my sample? So my list of numbers that I've taken from that box, that's my sample. So the sample SD is about that variability. The spread of the numbers you selected out of your sample from the average of your sample. Okay, guys, you've all taken your samples? All right, so, yes? Times the FPC. So the actual formula, which would be good to make sure that you know, is the actual sample SD is the box SD, or your population SD, divided by the square root of your sample size. Then the whole thing times your population size minus your sample size over your population size minus 1. That's the exact standard error of the sample average. We don't know this piece, the box SD, so we plug in the sample SD for it. Now, again, I'll be really repetitive. The box SD, or your population SD, is calculated by taking all of the different values in your population and finding out what's their average deviation from the population average. So it's the square root of the average squared deviation from the population average, which we don't know. So we don't know all the values. We don't know the population average, so we can't make that calculation. So instead we do it on the sample SD. So we have 1 minus 0.31 squared plus 1 minus 0.31 squared. We have 5 of those. Then 0 minus 0.31 squared plus 0 minus 0.31 squared. We have 11 of those. We add them all up and divide by 16. That's my sample SD. You're now free to eat the candies if you like, so you can pass them around, take whatever you want. But what we're going to do is we're going to collect your information about about what did you get for your population average, and what did you get for your estimate for your SD of the excuse me, what did you get for your sample average, and what do you get for your SD of the sample average? So before we go there, there's one other calculation I'd like you to make. So hopefully at this point you've made these two calculations. You've computed the average for your sample, and you've approximated the SD for the sample proportion sample average. Okay? Now what I'd like you to do is turn that into an interval estimate for the population average. So essentially what I want you to do is this. I want you to take your estimate. 0.3125 was mine. Not all of you got 0.3125, I'm sure. take the error that you have that's associated with that. Mine was 0.11. My guess is yours are all probably pretty close to 0.11. And create an interval estimate. So the 0.3125 is a point estimate. It's one particular value. But we're going to take our error that's associated with it and create an interval. So we take our 0.3125 and we add 1.96, or roughly 2, times the standard error, and we subtract 1.96 times the standard error, and that gives us an interval. And so we can use that interval as an estimate as well. We can say, in this particular case, with that size interval, I say that I'm 95% confident that the population proportion of yellows is in this interval. Okay? What I'd like you to all do is make your interval right now, and then we're going to see what all the various intervals there are, and then we're going to talk about what on earth this interval means. First you, and then you. Good question. It's really close to 2. And there's a connection between the 95% and the 2. Do you know what that connection is? 2 standard deviations on either side of the mean is 95% of the area under the normal curve. So that's coming from the central limit theorem that says the sample proportion should have a roughly normal distribution, and plus or minus 2, in fact it's 1.96, not 2, to 2 decimal places, plus or minus 2, or 1.96 standard deviations gives us 95% of the area under the normal. And that's where that's coming from. And we're going to cover that more in a second. Yes? That was, hopefully you got a number similar to what I got, but that was based on this calculation of the standard deviation of the sample proportion. So that's the SD of my sample divided by the square root of 16 times the finite population correction factor, which is 0.91. I'm sorry? That's your error. Right, your estimate for your error, your sampling error. So most of you probably got something similar to that, maybe? The one I keep skipping by? Or that one? Did anybody look inside their population? What did you find? How many yellows? Did anybody attempt to count what was in their population? Did anybody determine the population parameter before they started eating the starburst? No? Not one of you? Well, this is a very special case where we can actually see our population. So I spent a long time yesterday creating your populations. So let me show you what your population is. That's your population. There were 66 non-yellow starbursts in that population of 88, and there were 22 yellow. So for 22 divided by 88 is 0.25. So your populations were all identical in that they all had the same size and they all had the same number of yellows. They were not the same in terms of the numbers of orange, reds, and pinks. Do you guys want some? No? It's too early. You can take it. You can put it in your pocket and save it for later. So that's the truth which we are unable to see, except in this case we can if we had bothered to look in the population before eating it. All right, so what I'd like to now get is take my interval. Oh, so now that I've given you what's in the population, as many of you pointed out, you know that this follows the actual hypergeometric distribution. So we can, in fact, compute the exact probabilities of each of these proportions. That's what I've done here. So I've taken each of the possible values and made a little bar for each possible value so that the area of the bar corresponds to the probability of getting that particular value for the proportion. And I then took the normal curve, something that you've done in your homework assignment, and I superimposed it over the exact probability distribution. And you can see that even though we only drew 16 candies from our population, that already the normal curve looks pretty good as an approximation for the sampling distribution of my sample proportion. So the bars stand for the probability of getting a particular proportion. So just by raise of hands, how many people got exactly 0.25? So a few of you did. How many of you got what I got, 0.3125, or 5 candies out of 16? Did nobody get that? No one got 5 aside from me? Okay. How many got more than 5? How many got 6 out of 16? 1? How many of you got fewer, like 3 out of 16? A lot of you, okay. So you can see here that getting 4 was the most likely thing. Getting 3 was also quite likely. Getting 5 was pretty likely. And getting 6, so it is possible with a sample that has 1/4 starbursts out of 88 in a sample of size 16, those are the chances of getting those particular proportions. And they're related to how many yellows are in your sample of 16. So what I've asked you to all do is come up with what we're calling a confidence interval, and I'd like to hear you give me your confidence intervals, and I'm going to try and plot them over here on the document camera. So in other words, we know that the truth in this case is 0.25, and my interval was from 0.09 to here's mine. Was from let's see. I'm trying to figure out. I'll just do it like this. That's my interval. Somebody else? Can you give me your name and your interval? Yes? Dan. 0.21. Okay. Somebody else? Name and interval? Yes?
My name's Christina, and our confidence interval was negative. It was negative 0.0453
To what?
to 0.1703.
Okay. So, Christina, there's yours is below your name, but yes. Somebody else? Yes?
Cal. And ours was negative 0.03 to 0.41.
Really? Okay. Negative 0.03 to 0.41. Okay. That's Cal's. Somebody else? You could have gotten the same one. I want to hear all of yours, even if it's already up here. Yes? Name first. David?
0.015 to 0.359.
Okay, so what was your actual value? How many yellows did you get? 3. So that would be 0.316, which is, that sounds about right. Did anybody else get 3? Did you have a similar one to David's? 0.01 to, yes? So yes, so you're rough, that sounds good. And your name? Hello? So Sonia and David have the same. Anybody else get 3? Tell me your name and what interval, and I'll write your interval up here. I know more of you got 3 than this. A whole bunch of you raised your hands. Jeff, what's your interval? You got 2? So you're probably like, Christina, how many, where's Christina? We got 1. You got 1, okay. So 2 is 1/8, which is 0.125. And roughly your SD is probably 0.11, like mine was, close. Right, so let's say it's roughly 0.11. And so you got, where are we? 0.125 plus 0.22 is, yeah, so you're up, right, so you're like this. Or maybe, anyway, you cover. Anyone else? So notice what's going on here is that you're getting different values for your sample proportion. And then you're making a larger interval, or you're making an interval that's centered at your sample proportion and goes out 2 standard deviations or 2 standard errors in either direction. So even though you got only 2 out of 16, your interval actually includes the truth of 0.25. If you were unlucky enough to get 1 out of 16, your interval doesn't include the 0.25. If you got 5, like I did, it does include it. Somebody got 6. Who got 6? You got 7. Did you compute your interval? What is it up here? Oh, you're with Dan. You're the first, and so you still covered it as well, right? So. So this is what's going on here is you go and you compute your interval. So if Christina was the only person taking this sample of this population, she would say, I'm 95% confident that the true population proportion is in my interval. She's 95% confident, but she's wrong. It's not in her interval. But she doesn't know that because she doesn't have a chance to look in her population. So that's what this 95% confident means. It's not about the chance that the population parameter's in the interval or not. It either is or isn't. She's taken her sample, she's constructed her interval. It's a fixed interval now. And either that 0.25's inside it or not. So where does the 0.95 come from? Did you have a question? No. So let me show you. I did a simulation very similar to the kinds of simulations that you have all done. And let me get to it. So here's the confidence interval is an interval estimate of the unknown population parameter. We take the sample average, we go plus or minus some number of standard deviations or standard errors for that sample average. That number can be any one you want. If you choose 1, then you have a 68% confidence interval. If you choose 1.96 or 2, you have a 95% confidence interval. If you choose 3, you have a 99.7% confidence interval. And these percents are coming from the normal distribution, or the central limit theorem telling us that the sample average probability distribution is roughly normal. So what does that mean for an actual confidence interval? We say that we're 95% confident that the true population average is in our interval. This means that approximately 95% of the time, when you take a sample, compute the average, compute the standard error for the average, create a confidence interval by going out plus or minus 1.96 times your standard error on either side of your sample average, that 95% of the time when you do this, the population average will be in that interval. So can you imagine how you would check that this is the case if you were using R? Yes?
Wouldn't you replicate it 1,000 times?
Yes.
And then
Yes.
see if it came out 95% true?
Exactly. You would replicate it 1,000 times, for example, each time taking your sample, computing your average, computing the SE, making the interval, and saying, well, is it in there or not? Repeat that 1,000 times, and how many do you think would have the answer yes? 95%. So I did that. But I only did it 100 times. So I use the replicate function to 100 times draw from that population. Each time getting a certain number of yellows, and my sample size is 16, computing my proportion in my sample, computing my estimate for the standard error for the sample proportion, making the confidence interval. And take a look. Those are 100 confidence intervals. And yes, there's 6 red. Why are they red? They're red because those are the ones that do not include the truth. So that's pretty good. Roughly 95% of my 100 confidence intervals don't include or do include the population parameter, and roughly 5% don't. So that's what's going on with confidence intervals. So when you read about confidence intervals, when people say I'm 95% confident, you'll see this in those polls, like the election polls. You'll see in all sorts of survey results. When you're quoted, when they say that they are 95% confident, or this interval is a 95% confidence interval, that roughly means that 95% of the time, if I were to do this over again, many, many times, 95% of the time my interval would include the true population parameter. It doesn't say where it is in that interval, and it doesn't say if this is one of those 95% times or one of the unlucky 5% times. So you don't actually know if the true population parameter is in your interval. And that's why we say we're 95% confident that it's there. But we might be the unlucky situation where it's not. So that's essentially the whole idea that's behind sample surveys, is that there's some population out there which we would like to know something about. But we can't observe every single unit in our target population. So instead we take a sample using probability mechanisms. That the probability mechanism allows us to say our sample looks like the population. I'm going to use estimates based on my sample for the population. And I can even compute the error in the probability distribution related to my estimate because I've used this probability technique. So several of you are working with samples for your projects. Those of you working on the radon, those are simple random samples within counties in Minnesota. What you're interested in is the average radon level or the proportion of homes in that county that exceed the EPA recommended guidelines, or the average radon level, one of those two things for each of the counties. Another is the risky behavior. That's a sample as well of adults and what their practices are. From there, you want to make some kinds of estimates for what's going on for the population at large. Yes?
Kind of a different question. I was wondering, is the 95% confidence interval still applicable if you have like a really large population and you take a really, really small sample?
Very good question.
Or is it just like the interval is going to be really, really large, so it's not really helpful?
No, that's a really great question, and you're probably going to get to that on your homework. But let's answer it now. So the question is, what's the relationship between the size of the population and the size of the sample? Is essentially what you're saying, right? And so if we think about where does the population size come into play, and where does the sample size come into play? We know that. So I'll make 3 statements. We know, first of all, that it doesn't matter how large our sample size is, as long as we've taken a simple random sample, we expect the expected sample average is the box average. So that's good, no matter how small or large your sample size is. That's because of the simple random sample process. So what's the estimate for the spread, the error that's going on with your sampling process? We've seen that the law of large numbers tells us that the spread in the sample average is like the box SD divided by the square root of the sample size, then times the finite population correction factor. So let's take those 2 pieces separately. So the finite population correction factor, if you've got a humongous sample, or excuse me, a humongous population, what happens to that finite population correction factor for a reasonably sized sample? It's just 1, or it's really close to 1, and you basically ignore it. So lots of times you don't even know what your population size really is, but you know it's so big you can just ignore the FPC, the finite population correction factor. Even with our sample of 16 from a population of 88, that FPC was already 0.91, right? So you can imagine a population of, for example, Berkeley students of 30,000, taking a sample of a few hundred, you can just ignore that. So it's the same thing as saying drawing with or without replacement, it doesn't matter because my population's so big relative to my sample size. Then the other place where something comes in is dividing by the square root of the sample size. So essentially it says it doesn't matter how big my population is. The accuracy is all determined by roughly 2 things: the SD of the box, the spread in my population, and the square root of my sample size. So whether my population's 30,000 or 300,000, what's really driving it is the square root of my sample size and the population SD. Because those are both huge numbers, and if I take a sample of 100 or 1,000, either way the FPC's ignorable. And my gain is simply in the 1 over the square root of the sample size. That's a really good question. Did I answer it well enough?